Once you have the board evaluation algorithm, the next big question is how do you test it? How do you make sure that the algorithm responds correctly to changes in transition of the players, of the actors, of the roles, of the object it's tracking? One element is boundary condition. So, how does the scoring engine using the board evaluation algorithm change or score at start of the game, at end of the game, at middle of the game? And these changes in the board evaluation results, the scores that you creating, calculating, generating, and tracking, do they reflect the stage of the game that you expected to see? Do they reflect the differences that you expected to see? That's one part. Second, if you think in terms of transition effectiveness, the state is changing and the board evaluation score is also changing. But if you think in terms of the scale of the transition, so you've gone from a point where a game is evenly tied to a point where one player has a clear lead. Does the board evaluation algorithm reflect the fact that the stakes of the game, that the win probabilities for both the players have changed significantly? So that's two. Third is information compression. Does it compress everything that we need to capture as part of capturing the essence of the game and the transition in the states and the stages of that game? Fourth, what exactly is it that we're tracking? So one thing that we're tracking as far as the signal is concerned is probability of winning. This is key, right? This is the element that we want to get. So whatever number or score we generate, we want to calibrate that number to a probability scale that goes from 0 to 1. The score that the algorithm generates can be positive or negative. The probabilities need to be between 0 and 1. So if you think in terms of the distribution of the score could be all the way from, let's say, minus x to plus x, but the map of this distribution to the probability distribution has to be between 0 and 1. So the score may be from minus x to plus x, but that score when mapped to a probability distribution has to be between 0 and 1. The probability winning, lowest probability winning is going to be 0. It's not going to be negative. The highest probability winning is going to be 1, right? So this mapping has to be done. We haven't done that in the pre-release. We didn't do that in the quiz, but this is something that you have to think about when you think in terms of mapping what you've learned here in this stage of the course to thinking about how to build a game AI for the Scrabble engine. And this mapping essentially refers to what we call scale and calibration. So you need to scale and calibrate your scores to the correct probability numbers that represent the state of the game that you want to reflect. All of this together represents a collection of test ranges on which both the game, the board evaluation algorithm, the scores generated by the algorithm, and the probability of winning and losing need to be tracked and tested. How did we come up with the board evaluation algorithm? We simply looked at states and their transition. We looked at what are the key drivers that have a direct impact on the state of the game and play a key role in how those states transition from one stage to the next. Then we converted those drivers into metrics. Then we converted those metrics into a score. And then we tried to test that scoring mechanism on how the board changed and whether the score changed accordingly. So the question you have to ask yourself is, how does the board change and who are the actors who play a role? The actors that we identified in this specific instance were tiles on the board, the special squares, the high scoring tiles remaining, and the score differential. These four components to us in our first pass did a reasonable job of tracking the performance, the win probabilities for both player 1 and player 2. So when you apply the board evaluation algorithm to the time travel challenge, one quick test, and this is a very simple, easy test, right? Which one of these words, given the choice to play, which one of these words should your board evaluation algorithm favor? So if you look at ahead, what is the total score of the word ahead? What is the total score of the word trade? What is the total score of the word bold? And what is the total score of the word zips? Now let's assume that zips the high scoring word. And let's also assume that zip is right next to, you're going to play this on a triple word score. So ideally your board evaluation algorithm, when you use it to identify the right path here in this specific site, shouldn't bring you to bold. Ideally, your board evaluation algorithm should actually get you to a point where it picks this stage because this stage gets mapped to zips, then it picks this move, then it picks this move, then it picks this move, and finally it gets you to the move that gets you to play zip. That's a good test. The other point that this represents is essentially what you're doing. You're saying, I have this tree has a lot of paths. These are all paths, has a lot of paths. I am searching for the most possible optimal path that can exist, that can lead to the highest possible score. So building the tree, expanding the tree is part of your problem space definition challenge. Finding the right move, the right solution within that tree is a search problem. Problem space definition and search. These are the two themes that we've spoken about again and again, both in our conversations with you, that within the field of computer science, the two things that you need to get good at are problem definition, your ability to define a problem space, to define it correctly, to define it accurately, define such a fashion that it captures the essence of the problem space, and then to search for a solution within that problem space. Two challenges, two key skill sets: search, definition, or counting. And not just any search or any counting, but searching and counting effectively given the parameters defined as part of your challenge. If you think about the word generation problem, the way we approach the word generation problem was anything but efficient. It goes back to the point that I made earlier at the start of this class, that sometimes we have to do things the wrong way to really appreciate how right the right way is. Search and problem spaces is one of the last, but it's also one of the most important items on our list of lessons, list of takeaways that we want you to remember when you look back at quiz 1 and quiz 2, when you look back at week 1 and week 2. Here's a plot of the total number of filtered combinations that were generated by your word generation algorithm and the number of valid words that were generated by the word generation algorithm as validated against both the Oxford and Collins dictionary. So if you look at 7-letter words for a given slate, I haven't shared the slate here for you, but for a 7-letter word, about 10,000 plus combinations were generated and none of those combinations were valid. For 6 letters, about half as much were generated, but only one was valid. For 5 letters, about half again were generated and 7 were valid. 6 with respect to Collins, 1 with respect to Oxford. 840 and 32 with Collins, 210 and 41 with Collins, 42 and 18 with Collins. Now, if you see the plot, this blue bar is the number of filtered combos. Filtered for replacements, for duplicates, for blanks, for adjusting and adding conditions that allow for sampling without replacement. So as you move forward, as you move from 2-letter words to 7-letter words, this goes up. But interestingly enough, the yield, where yield is defined as a valid word within either the Oxford or the Collins dictionary, as you move up on this side, as you increase the dimensions, the number of elements, you find that the yield for valid word goes down. And this reflects and represents a common problem when we look at searching spaces, especially problem spaces. As you add additional dimensions, you will find that your problem spaces will increase in size. You will also find that the yield of solutions to those problem spaces will also go down. So you have a double challenge. First, you're searching a much bigger space. 2, within that much bigger space, the number of valid data points, the number of solutions, the number of coordinates and metrics that will actually lead to a answer to the challenge you're seeking will go down. That's one. Here's another representation of the same data. This representation actually tracks yields, and it's reflecting the same concept but in a slightly more legible, readable form. Once again, this side is the number of word combinations that are generated. As you go from 2 letters to 7 letter words, you can see that goes up, and this represents the yield. So yield goes up as the number of letters in the word combination goes down, but at the same time the number of possible letters generated also goes down, and yield goes down as the number of letters in the word combination goes up. It goes down simply because you're searching for a valid combination, but also because a lot of the combos you're generating are gibberish and garbage. If I summarize the point that we've made, search spaces are broad and wide. Yield gets lower as search spaces grow, which basically means that search efficiency is key. Search, the reason why you'll spend a lot of time looking at trees and lists and algorithms for search is because search efficiency is key. Within the field of computer science, if you think in terms of interviewing at any place that hires decent engineers, you'll find that you will be tested on your mastery of the search algorithm. So spend a lot of time on search. Now, what is efficient search? How do you make search more efficient? You have to start by identifying where you want to look. If you start at the right place, if the starting point in a given problem space is correct, then you already have an advantage over everybody else who does not know or is not aware of where the starting point is. Indexing on starting point. So if you think in terms of a dictionary, you can search a dictionary word by word, you can search a dictionary by the other method, but it really help if you can sort the dictionary and index it on the first letter. So rather than doing a word match from A to Z, all the way from A to Z, it would make sense if you can just go straight to Z or Z when you see, or X or Y when you see a letter that begins with Z, X or Y. Dimensions lead to combinatorial explosions. So the more dimensions you have that are part of your problem definition, the bigger the problem space you're searching. It would help for you to simplify your definition of the problem space. Hence our emphasis in both week 1 and on week 2 on simplifying, on spending time, on identifying every aspect of the challenge, the problem you're trying to tackle and attack, and then drilling it down, dialing it down to its essence. So it's two components, two concepts at play. One is problem definition and the second is information compression. If you can use one dimension to define the problem rather than 3, use one dimension. It'll reduce your problem space and it'll make your search and your yield much faster. I think the most important point, but it's not the most obvious point, and this is something that a lot of you struggled with. I think the most common feedback or comment that I got as part of when I was watching the WhatsApp group explode with respect to comments and suggestions, as all of you struggled with the pre-release and trying to figure out how to address and solve the pre-release. I think the biggest comment that I saw was Excel is freezing, my laptop is hung, my sheet has crashed, I've lost all my work. Theoretically speaking, we think about this, validating, let's say, 10,000 words against 280,000, validating 10,000 words against, let's say, a 280,000 strong dictionary shouldn't require you to have 8 GB of RAM. It's a simpler problem, much simpler, much easier problem. But why did it take? Why did it cost? Why did it took so long? Technically speaking, validating a 10,000 word list against a 280,000 strong word bank shouldn't require 4 to 8 GB of RAM. The numbers sound big, right? 10,000, 280,000, but they're not as big as a problem that would require you 8 gigabytes of RAM to solve. And yet this was a challenge. Why is that? It was a challenge because as part of our work ethic, there was a time when our work ethic emphasized conservation of memory, respecting memory, using memory in a very memory efficient fashion, but those times are long gone. One of the key points that you should have picked up was that you may have had the fastest of all processors, But if you didn't have enough RAM, if you didn't have enough memory, that processing power was worthless. As a developer, as a programmer, as a computer science student, the takeaway for you is respect memory. We may think that we may have a machine that has 8 GB, 16 GB, 32 GB, or 64 GB of RAM, but RAM always runs out. RAM runs out because RAM is always in contention. Assume, even if you have infinite RAM, assume that you'll run out of it. Which then basically means that when you sit down and write code, don't assume that you will have infinite RAM. Assume that memory will run short. And usage of memory as far as your code is concerned should be as efficient, should be as respectful as possible. Which then, essentially suggests that there must be alternate paths, better paths for both search, storage, and word generation when it comes to Scrabble. And where would you find these? You would find these in the readings of the course for week 2. So if you remember, fastest Scrabble program in the world, or the shorter form of that is, the fastest Scrabble program in the West. That article, that piece, it's a very small piece, but it's a seminal piece. It talks a great deal about how we search, validate, generate, and verify words can be simplified down to a simple structure that is not just memory efficient, but also very, very fast. There are few things that should be apparent to you now that you've gone through both the pre-release, you've built the word generation algorithm, and you've gone out, tested it, and taken the quiz on it. How we've done word generation is not how word generation should be done. And the reason for that is very simple, because we've now seen how clunky, slow the brute force approach is. The approach that we used was a brute force approach. The approach that we use is a brute force approach. We just took every possible combination and we just listed it out. That's not how it's supposed to be done. So there has to be a better approach. But what is the problem with the brute force approach? One is the combinatorial explosion. So, with 7 words, you're already at 10,000 plus. What if you need to do 10 words? What would this number be? It's not just the combinatorial explosion, it's also the low yield of valid words when we look at the combination that were generated. So a lot of the effort, the time, the memory, the resources that we spent in generating those combinations went to waste because there were very few or zero valid words in the word generation combinations. How do you fix that? You fix that by looking at how the fastest Scrabble program in the West addresses that question. So if you haven't read it, or if you read it initially before you did the word generation problem, read it again and get a sense of what is it that they did differently that was so different from the approach that we've used. Remember, sometimes we have to do things the wrong way for us to appreciate how right the right way is. I think the second last item on my list is dictionary word validation. There were 2 specific functions that you're supposed to use. One was VLOOKUP, one was IF-NA, and you use them in combination to get the end result that you needed and wanted as far as your word validation algorithm was concerned. Some of you did use Power Query, and while there is nothing wrong with using Power Query for word validation, when you went from 10,000 words on the Oxford Word Bank to the 280,000 word on the Collins Word Bank, a lot of you ran into trouble with Power Query for one simple reason, and that simple reason is overhead. The overhead for Power Query in Excel is much more significant than the overhead for VLOOKUP. It's not that VLOOKUP is any more memory efficient or VLOOKUP is any more better, but as far as when it comes to scaling up your exposure from 10,000 words to 280,000 words, you'll find that VLOOKUP wouldn't break your system, but Power Query would, especially for systems, especially for machines that had lower memory. I have an example. Let's take a look at it now. All right, so word validation, the word validation example. How do we fix the word validation challenge in Excel? So as part of your week 2 pre-release, you were given a sheet called week 2 assessment sample output. And in that week 2 sample assessment output, you'd see that there was a list of 4-letter words, 3-letter words, and 2-letter words. And against that list, there was a column. And this column had mostly zeros, but somewhere in there was a couple of ones. So mostly zeros, and there's a one here and there's a one here. Now if you click on this cell that says 1, you'll see a formula. This is a formula for word validation. The formula has two pieces and two parts. But before we dig into those two pieces and two parts, what I want you to do is I want to trace it. In Excel, there's a very simple way of tracing a formula. All you need to do is click on the cell and then go to the formula tab here, and then in the formula tab say trace precedent. When you trace precedent, it actually shows you where the formula is heading, the field and the numbers it's using, and the direction it's going in. So I'm going to sort of zoom out a bit, and then what I want to do is I want to click on this again so you can actually see. So if you now see the reference, you can see that the formula has two pieces. The first piece of this formula is if NA. So if NA refers to the fact that if VLOOKUP searches, what you see here is VLOOKUP is searching in the dictionary. This is the Oxford dictionary, and in the Oxford word bank, it is looking up a cell. Which cell? It's looking at this cell that says NE. And when it looks for this cell called NE, it is essentially saying look up cell number I25. So this is I. You can see it refers to I25. This cell here is I25. It's looking at this range. So if you see you can see that VLOOKUP is referring to I25. This is I25. This cell is I25 NE. And where is it looking? It's looking at NE in this specific range. This blue line represents this range, and this is the Oxford word bank. And it's looking for column number 2. And column number 2 has a list of ones. So what we've done is when you do a lookup will simply say, okay, I found this. But then what do you want from that finding? What you want from that search result is, if it's successful, give me the number 1. And if it is not successful, give me the number 0. How do we do that here? If VLOOKUP finds a match, it will return 1, which is this part of the formula. There you go. But what if VLOOKUP doesn't find anything? If VLOOKUP doesn't find anything, it will return the word or letter called NA, which is not available or not applicable. Once it gets NA, you know for a fact that a match was not found. So for that, we use the function FNA. And what FNA says is, if you find a result, you will return 1, which is a valid value. So if it's a valid value, just give me the valid value. But if you find a result which is not valid, then what do? Then you give me the value which is if NA. And the value that we've picked up for if NA is 0. So the way the logic works is, the logic says, if I find a valid value, what do? I give you 1. How do I give you 1? Because VLOOKUP will return a 1. Why does VLOOKUP return a 1? VLOOKUP searches this word NE in this list. If it finds NE, it'll find the value against NE in column number 2, and column number 2 is a list of 1. So if I find a result, if I find NE, I will return 1. If I don't find NE, what will I do? I will return NA. NA is not available. And then on this, I do a second decision. So, okay, if I find NA, then what do? If I find NA, then I write 0. And if I don't find NA, then what do? I simply put in the value that has been returned, which is the letter 1. That in essence is the logic for dictionary validation. That's how you're supposed to do it. I know some of you use Power Query, and that was a much more elegant and graceful fashion, but that only worked if you had enough memory, if you had enough processing power. There was still a couple of tweaks and challenges that you would run into when you refreshed your slate, and that was the risk with Power Query. But with word validation, when you refresh your slate or you refresh the dictionary, all you had to do was change and update the formula references once, and you would be fine. And that covers our review of the word validation function. All right, so parting words. We started this session with a list of non-CS lessons. I want to finish this session with another set of non-CS pointers that I hope you'd remember and that you put to work in the remaining part of this course. One, if you're offered a retake, take it. So even if you have the highest score in the class, take the retake. Retake is a great opportunity for you to understand the search space better. understand problem sets that test the search space, and even understand your ability, your own limitations with respect to that search space. So never let go of an opportunity to explore problem spaces, even when that means taking a quiz that you already taken and you already scored a reasonable score, because you don't know what variation of challenges and problems you're likely to see in the questions that have been selected in the retake test bank. At a personal level, it generates an additional data point for you to look at. It gives you better sense of how you react and change. And remember, retakes are harder. So if you do a reasonable job or a good score on a relatively easier version of the test, a retake can prove to you that you're just as good when the stakes are higher. Always good to have additional data points, especially when it comes to personal performance. Incorrect questions. My apologies for these. Mistake on my part. The word generation sheet that I'd used had a couple of errors, and those errors sort of blew up in my face. So yes, there are incorrect questions and answers in the problem set. I'm really, really sorry about those. What we're now doing is we're identifying all the variations that are incorrect in the problem set. We will rectify the scores. The process for that is going to be fairly simple. I think by the time we get to next week, we'll actually have TAs in place for all sections of the course. All you need to do is bring in your questions and your results to the TAs. They will verify and validate that the question that you saw, that you attempted, was in fact incorrect, and that your answer, the answer that you picked, was the correct choice and was scored incorrectly. Once we've identified all such variations of questions, we will give you a heads up that here are the TAs and here are the dates in which you can come in. You can come in, identify the variation that you took, identify the question that you took, identify the question that was incorrect from your perspective. The TAs will verify that that is indeed true, and if it is true, we will adjust your scores. This will happen post the third quiz. So there's a quiz this weekend. This will happen after the third quiz. There is a quiz this weekend on Saturday or Sunday. There are no quizzes on the 16th and 23rd weekend. 16th is the Google Developers Group at City Campus. We'd expect and want you to see there. 23rd is the Mindstorm Game Jam. So there won't be a quiz on 16th and 23rd. There's only going to be a third quiz this week, and then you have a 2-week break. Not exactly for rest and recreation, but certainly no quizzes. And that marks the end of the tutorial session for this week. I look forward to seeing all of you in class on Thursday and Friday.